So we're doing a review problem with question. So this is exam review 3, question number 7. So question number 7 says, find the magnetic field, run a wire carrying a current of 24 amps at a distance of 4.3 meters. Make sure to start deriving the equation from Ampere's law. So remember, we're trying to make sure you understand how to use Ampere's law. So we have here's our wire. It's carrying a current of 24 amps. So I'll leave it, actually, I'll wait amps. 24 amps, 24A. And it's at a distance of let's see, 4.3 meters. Find the magnetic field. Okay, so, well, it's not a vector, we're just finding the direction of the magnetic field. So Ampere's law basically says there's multiple ways of saying Ampere's law. The two laws, the ways I explained it, right? One is that if somebody gives you some kind of a field line, right, where the magnetic field is pointing in the direction of the tangent to this curve, so the magnetic field at every point is pointing tangential, and it's a constant uniform magnetic field, then Ampere's law says that B times the perimeter of that path, so let's call this L, this is the perimeter length, length of path, is equal to, so you have a uniform magnetic field, the strength of the magnetic field is constant along this path, then that's equal to something called the permeability of free space, some constant mu O, times the current that punctures the area that is bounded by this path. So if somebody gives you a path and they tell you the magnetic field is uniform along this path, it's always uniform, then B times L is equal to it's related to the amount of current that punctured the surface. So remember, so this is called Ampere's law. So this is one way of defining Ampere's law. And another way is I also did it in terms of the summation of BI dot L dot vectors. So I won't do that right now, we'll leave it for solenoid. But the second way of defining it, let me do it anyway, just in case. So the sum of a magnetic field along some path length is equal to the sum of all these path lengths, individual path lengths, that corresponds to some magnetic field I acting on some position length vector from here to here. If I sum all of these vectors together, it's equal to the amount of current that punctures the area that is bounded by this path. So these are both Ampere's laws. So we're going to be using actually this because if I take a current wire and take a cross-sectional view of the current wire, so here's our wire, it's coming towards you. So here's our current, we're carrying wire coming towards you. We know that the magnetic field lines, if I grab my right hand, use our right hand rule, and I grab it, you'll see that the magnetic field lines are going around like this. And so we expect that at every point around this wire, the magnetic field is going to be constant, so we can actually use our first law and ask ourselves, so if you're at a distance of r, what is the perimeter of the circumference of the circle? Which is the circumference of a circle, 2 pi r. So we're saying that B times 2 pi r is equal to the current that punctures the area that is delimited by this perimeter length, this perimeter of circle, which in this case happens to be mu O times I. So the magnetic field is given by mu O times I over 2 pi r. So we can actually plug in values. So mu is given as 4 times pi times 10 to the minus 7, which is a constant. So the permeability of free space called mu O is given by 4 pi 10 to the minus 7. the current happens to have a value of 24, 2 significant digits, and 2 times pi times the radius, which in this case happens to be 4.3 standard units, meters. And so whatever the answer is, we plug into a calculator, and the answer must be in Teslas. Teslas. T. I think I'm spelling. Actually, just let's just put T in, because yeah. Anyway, so the main idea is that we're using Ampere's law to construct the strength of the magnetic field around a wire. Okay, so hopefully you understood that.